Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at Bayes decision strategy. This will be an introductory treatment of Bayes decision strategy. There's a lot more that we could say about the topic. I'm going to first introduce the general concept and general technique, and then we'll do one example. This one example will have a result that is probably almost obvious to you right from the start, but that's okay. Sometimes doing examples that have obvious answers give us confidence that the techniques might work later on when we tackle more complicated problems. So, what is Bayes decision strategy? Bayes decision strategy is a formal strategy for choosing between two alternatives. Perhaps Bayes decision strategy could be extended to consideration of multiple alternatives. We, however, are going to consider only two. What we're going to do is seek to minimize the cost of making a decision. Okay? We're going to seek to minimize the cost of making a decision. Now the cost may or may not involve real dollars. Alright? Cost may or may not involve real dollars. However, most engineering decisions, I would say all engineering decisions, have financial consequences. It typically costs less for us as engineers if we make right choices. So I'll just say that as engineers, our choices, our decisions, at least have indirect financial consequences. All right. We are going to designate our two possible alternatives by in the following manner. We will designate our alternatives by capital H sub 0 and capital H sub 1. And we'll then define for costs as follows. C sub 0, 0 is the cost of choosing alternative H naught, H sub 0, when H naught is actually the best alternative. Alright, C sub 0, 0 is the cost of choosing H naught when H naught is actually the best alternative. C01 is the cost of choosing H naught when H1 is the best alternative. C sub 1, 0 is the cost of choosing alternative H1 when H0 is actually the best alternative. And C sub 1, 1 is the cost of choosing alternative H1 when H1 is in fact the best alternative. Okay? All right. Well, notice this. Typically, C sub 0, 0 will be less than C sub 0, 1, and C sub 1, 1 will be less than C sub 1, 0. The reason for that is that, typically speaking, it costs us less to make the right choice. All right? Okay? May not always be the case, but typically that is the case. All right. Now, I need to write down some conditional average costs. So, if H naught is the best choice, the conditional average cost of making a decision we'll designate decision with D is the cost of making a decision if H naught is the best alternative equals C sub 0, 0 times the probability that we actually decide H naught, we choose H naught given that H naught is best, plus C sub 1, 0 times the probability that we choose or decide upon pursuing alternative H1 given that H naught is best. All right? All right. The cost, C represents costs of making a decision given that H naught is the best alternative is C00 times the probability that we actually choose or decide to pursue alternative H naught if H naught is the best, plus C sub 1, 0 times the probability that we decide to pursue alternative H1 given that H naught is best. Now, if you take a careful look at this, you're going to say that this looks a whole lot like total probability. It is similar to but it is not a statement of total probability. And the reason that it is not a statement of total probability is because C00 and C10 are costs and not probabilities themselves. All right, so if this is confusing you, what I suggest you do is go way back into some of your early notes for this semester and look at the concept of partitioning a sample space and look at total probability. Similar to, but not quite equal to, total probability. All right, we need another piece of this equation. Similarly, if H1 is the best alternative, then the average cost of making a decision is this. The cost of making a decision, given that H1 is the best alternative, equals C01 times the probability that we decide H1, given that H0 is best, plus C11 times the probability that we decide to pursue alternative H1, given that H1 is actually best. All right? All right. Next piece of the puzzle. We're going to let the probability that H0 is best equal little p. That's a little p. And the probability that H1 is the best, we're going to let that equal little q. And little q equals 1 minus p. In other words, p plus q equals 1. One of the two decisions. Remember, we're tackling a strategy for choosing between two alternatives. One of those alternatives must be the best. All right, in this discussion. Okay, one of the two alternatives must be the best. All right. The overall cost then of making a decision can be written this way. The overall average cost of making a decision is therefore cost of making a decision, this is a non-conditional cost, equals the probability that H0 is the best times the cost of making a decision if H0 is best plus probability that H1 is best times the cost of making a decision when H1 is best. All right? Or little p times cost of making a decision given that H0 is best plus 1 minus p times probability that, times the cost of making a decision given that H1 is best. All right? So, let's expand all this out on the following page, and we get this. The overall average cost of making a decision equals P times C00 times the probability that we decide to pursue alternative H0 when H0 is best plus C10 times the probability we decide H1 given that H0 is best. Plus 1 minus P times C01 times the probability we decide H0, given that H1 is best, plus C11 times the probability that we decide to pursue alternative H1, given that H1 is actually the best. Okay? All right. All right. So C of D is the overall average cost of making a decision. All right, and what we do is we seek to minimize my average cost. All right. All right, we seek to minimize the average costs. All right, let's do an example. Let's do an example. We are going to have a digital binary data stream. Okay? We're going to assume that ones are represented by a 10-volt level going down my transmission line. And we will assume that zeros are represented by 0 volts. All right? So if we send a 1, we send a 10-volt pulse, and if we send zeros, we send nothing. All right? We're going to assume that white Gaussian noise corrupts the data stream between the transmitter and the receiver. So white Gaussian noise corrupts the data stream between the transmitter and receiver. We're going to assume that this is 0 mean Gaussian noise, and we'll assume that the standard deviation is 2 volts. All right? 0 mean Gaussian white noise with a standard deviation of 2 volts is going to corrupt our digital data stream. All right, at the receiver, our signal plus noise is compared to a threshold voltage T. All right, so at our receiver we detect our signal plus noise every clock cycle. We compare that detected signal plus noise to a threshold voltage T. And if the signal plus noise is greater than the threshold, we decide that a 1 was transmitted. And likewise, if the signal plus noise is less than the threshold, we decide that a 0 was transmitted. All right, so keep in mind, zero mean Gaussian noise can have positive voltage and can have negative voltage. So I can actually send a 1 with a 10 volt level and have negative going noise add in to push my signal plus noise lower than my threshold. That would cause me to declare a 0 when a 1 was actually sent. Likewise, I could have positive going noise, and that might add into a 0, and the noise alone might be above my threshold voltage, causing me to declare a 1 when a 0 was actually sent. All right, a couple of things. We are going to say that C sub 0, 0 and C sub 1, 1 are both equal to 0. In other words, there is no penalty for making a correct choice. If I send a 0 and declare it to be a 0, there's no cost associated with that. If I send a 1 and declare a 0, or send a 0 and declare a 1, that's 100% in error. I've got a digital binary data stream. If I send a 1 and call it a 0, that's 100% wrong. All right. Furthermore, I'm going to assume that P equals Q equals 1/2. And what that means is for long data streams, we send about 50% ones and about 50% zeros. All right, so about half the time I'm going to declare a 0, and about half the time I expect to declare 1s. That just kind of makes sense. And the question is, what is the optimum threshold? What is the optimum threshold? That's the question I want. That's a question I want to answer. What's the optimum threshold? All right. Let's simplify our total cost statement as follows for this particular example. My cost equals 1/2 times the probability that we decide a 0 was sent if we actually sent a 1, plus 1/2 times the probability that we decide that we sent a 1 if we sent a 0. Okay? All right. Remember, C00 and C11 were both 0, so those conditional probability terms don't show up in our result. All right. The next thing I want you to notice is that this half, this one, is the probability of transmitting a 1. This is the probability of transmitting a 0. And here I have conditional probabilities. The point that I'm getting at is all of the factors for this example, in the equation at the top of the page right now, for this particular example, everything on the right-hand side of the equal sign is a probability. It's a probability. So for this particular example, that cost is a probability. A probability. All right. Moreover, you'll notice that the probability terms up here are both errors. This is the probability that I make an error by declaring a 0 when a 1 was sent. Over here is the probability that I declare a 1 when a 0 was sent. So my cost for this particular example is the probability of making an error. So I'm going to designate this capital P sub E. And this is the probability of making an error, a decision error, at my receiver. So this is probability of error. All right, it's the average probability of error. Probability that I'm going to make a mistake at the receiver. The aggregate likelihood that whatever the bit stream actually is, I make a mistake. Call a 1 a 0 sometimes, call a 0 a 1 sometimes. Okay? So, let's pause for just a second and do a short review. Remember this. If I have a random variable x that is a Gaussian, x is a Gaussian random variable. M is the mean, and sigma is the standard deviation. And we'll assume that the probability density function for x looks something like this. There's the mean, and that represents the standard deviation. Let's pick a point here, x naught, and recall that the area of that shaded region the total area of any proper probability density function is exactly 1. The area above the area in the upper tail above point x naught is the probability that x, random variable x, is greater than x naught, and you'll recall that that's found through use of the Q function. That's Q of x naught minus m over sigma. All right? And you'll recall that early on I sent you a q.m m file for MATLAB. All right? That's how you find the area of the upper tail of a general Gaussian. We'll need that in just a couple minutes. All right. Back to our story. For our digital data stream, let's assume that at the receiver, each clock cycle, we detect a voltage Z, which equals A plus N. N is my noise, and A equals 10 if 1 is sent, and equals 0 if zeros are sent. Okay? Moreover, we're going to assume that my noise, as I said earlier, is zero mean Gaussian. So my probability density function for my noise is 1 over square root of 2 pi sigma e to the negative n squared over 2 sigma squared. Remember, it's zero mean. That's why my noise is centered at 0. So my mean equals 0, and sigma is 2 volts. All right. So let's piece this together. I need to find two conditional probabilities. The probability that I decide that I sent a 0, given that I sent a 1, equals the probability that A plus n is less than my threshold. In this case, I'm assuming that I sent a 1, meaning that A equals 10 volts. All right? If I decide a 0, given that I sent a 1, that's the probability that A plus n is less than my threshold voltage. Rearrange this a bit. This is the probability that my noise voltage is less than T minus A. All right? Now I want to make an observation. If zeros are represented by 0 volts and ones are represented by 10 volts, it makes no sense to me to set a threshold above 10, right? So if my maximum voltage that I send is 10 volts, it doesn't really make sense to declare a decision threshold that's 15 or 16 volts. If I do that, the overwhelming majority of times I'm going to declare all of my bits to be zeros. So, notice that in most cases, in virtually all practical cases, my threshold is going to be less than, my threshold is going to be less than A, so that T minus A is less than 0. Okay? Let's go to the next page. Let's sketch out my noise voltage probability density function. Zero mean Gaussian, and this will be T minus A, a negative value. All right. This area down here is the probability that my noise is less than T minus A, keeping in mind that T minus A is a negative number. By symmetry, however, By symmetry, the probability that my noise is less than T minus A equals the probability that my noise, let's make that a capital N, that my noise is greater than A minus T. All right? And this equals, from the review just a minute ago, Q, because I'm zero mean, A minus T over sigma. All right? So there's that. The probability that we decide 0, given that we sent a 1, equals Q of A minus T over sigma. All right? Let's go to the next page. We also need to know this. The probability that we decide that a 1 was sent, given that we sent a 0. In this case, this is going to be the probability that the noise alone is greater than the threshold, meaning that in this case, capital A equals 0 volts. All right? If we send a 0, A is 0. And if we declare that there is a 1 present, that's the probability that my noise alone is greater than my threshold. So once again, looking at my probability density function for my noise, that's 0. Here's threshold. This is the area. That's the probability that the noise is greater than my threshold. And using the Q function, this is Q of T over sigma. Once again, my noise is 0 mean, so I don't have to subtract off the mean. All right. Therefore, after all is said and done, we plug this back into our relationship for a couple of pages back, and we find that the probability of error equals 1/2 times Q of A minus T over sigma plus Q of T over sigma. All right, and what I then did was I plot the probability of error versus threshold for A equals 10 volts and sigma equals 2 volts. 2 volts. And my result is the following. All right, that's this guy. Remember, A here equals 10 volts. Sigma equals 2 volts. All right, and what we find is that, not surprisingly, if this is the voltage that I send when I send a 0 cent, and this is the voltage 10 when I send a 1, the optimum decision threshold, this is where I said earlier it's probably quite obvious to you from the beginning, my optimum decision threshold is right in the middle. It's 5 volts. The optimum decision threshold is 5 volts. Okay? But minimizing my probability of error doesn't mean that I eliminate errors. So if you stretch this over, in MATLAB I used the minimization function. The minimum probability of error, is 0.00621 or 0.621% in this particular case. All right? About 6/10 of the time, I'm going to be making a mistake when I have a digital data stream represented by 0 volts for zeros and 10 volts for ones, when I am corrupted by 0 mean Gaussian white noise with 2 volt standard deviation. All right. I claim to you, without justification, that this is huge. All right. For RF data, in other words, your cell phones talking to cell towers, for radio frequency data communications, we typically like to have probabilities of error less than about 10 to the minus 6, meaning that 1 bit in a million is in error. For optical fibers, we typically like to have probabilities of error that are less than 10 to the minus 9, meaning that 1 bit in a billion is in error. In any event, the question at hand for this particular example was to determine the optimum decision threshold when 1s were represented by 10 volts and 0s represented by 0 volts. The not particularly surprising answer is that my optimum threshold is 5 volts. All right. Well, that's all for my introduction to Bayes' decision strategy. As usual, if you have any questions about what I've presented, please do contact me at your earliest convenience, and I will be happy to answer any and all questions as fully as I am able. Have a nice day. Bye-bye.